Hello, I'm Steve Temme, the founder and president of Listen. Today I'm going to introduce our newest measurement algorithm, Enhanced Loose Particle Detection, or eLP. Last year we launched our new perceptual rub and buzz algorithm, ePRB, and this new eLP algorithm goes hand in hand with ePRB to fully characterize audible defects on the production line. As some of you probably know, perceptual measurements are Listen's area of expertise, and one of my missions is specifically to make it possible to correlate automated measurements with what you can hear. Although this new method is not a perceptual algorithm as such, it's very easy to compare graphical results with audibility for a better understanding of the measurement. In this short product launch, I'm going to first start with a little background on loose particles or transient distortion and why it's important to measure. I'll talk a little about prior measurement methods, both from Listen and others. Next, I will walk you through our new algorithm and explain how it works. Finally, I'll demonstrate some results, and we'll have time for any questions at the end. So let's start by taking a look at transient distortion. Transient distortion is caused by random rattling, clicking, and other noises. In a speaker or headphone driver, this may be caused by debris such as glue or magnet fragments trapped behind the diaphragm, or a dust cap, otherwise known as crap in the gap. In something like a smart speaker, transient distortion might come from rattling buttons that vibrate when sound is played. In an automotive application, it could be characterized as buzz, squeak, and rattle from loose wires, screws, or fasteners. Whatever the cause, it's usually introduced at the manufacturing stage rather than by design, and of course, it makes the device sound bad. So any product with transient distortion should be identified and rejected. Let's listen to an example. I'll play you a speaker with loose particle distortion here. Do you hear that rattling noise? Let's listen to a good speaker now. And now the bad one again. Can you hear the difference? Hopefully you heard the loose particle distortion in the bad speaker. Now let's look at the waveforms for the bad speaker. You can see the transient distortion faults appear as impulsive noise on top of the stimulus wave. These impulses are not related to the frequency of the stimulus, but rather to the vibration caused by the displacement amplitude of the diaphragm. The transient distortion is more frequent and significant when the speaker is driven near or below its resonant frequency, where the displacement of the diaphragm is greatest. Now, you probably know that most speaker measurements are made in the frequency domain. But if we look at the corresponding frequency spectra for these waveforms, you can see this line here is the stimulus frequency, and this noise here is the transient distortion. And looking at it like this doesn't really give you useful information. This is different from periodic distortion, where the defects would show up as a series of vertical lines at the harmonics. So although periodic or rub and buzz distortion is best identified by the frequency at which it occurs, transient distortion is best identified at the time the transient occurred. There are measurement methods that actually measure loose particles and periodic distortion together, but we recommend measuring them separately as they are caused by completely different mechanisms. Before I jump into the details of the new algorithm, let me give you a bit of background as to the current state of the art. There are two methods commonly used for transient distortion measurements today. The first is our 2004 loose particle algorithm. We first introduced the concept of using time analysis to measure transient distortion at an AES conference back in 2003, and this was refined and introduced into the soundcheck software in 2004. This early model used a time envelope analysis method, which is widely used for detecting faulty bearings and gears in the machine industry. We were the first people to use this technique for audio quality measurements, and we made several adaptations for this new application. We used a sine sweep stimulus and then applied a tracking high-pass filter and RMS envelope analysis to the response waveform. Within this envelope, we then detected and counted the number of transient events. This was the first method that separated transient distortion from periodic distortion and is widely used on production lines, primarily for driver manufacturing. Of course, it's not perfect. Faults can be hard to discern under certain conditions. Also, it can be complex to configure and set limits because there are several variables that must be balanced to optimize results for each product and test environment. Another approach to loose particle detection is crest factor analysis. This method uses a tracking high-pass filter and examines the peak to RMS ratio, or crest factor, of the waveform. Sine waves have a low crest factor of 1.41, but transients typically have a crest factor greater than 10, so this makes them easy to spot. Harmonic distortion artifacts also have an elevated crest factor, so this method identifies both types of distortion together. This single distortion metric can be useful for production line pass-fail testing, but it does not reveal the precise failure mode and is susceptible to background noise, which also has a high crest factor. This is important as transient and periodic distortion are caused by very different mechanisms. In a speaker driver, periodic distortion, often known as rub and buzz, is caused by a rubbing component. For example, an improperly centered voice coil or poorly glued components, such as the surround or spider. Transient distortion is caused by loose particles becoming trapped under the diaphragm or dust cap and rattling randomly with the movement of the voice coil. It can also be caused by loose buttons or other rattling components. If your devices start failing distortion test, it's really valuable to know whether you have a rub and buzz or a loose particle problem. This tells you where to look for the root cause so you can fix the problem quickly without incurring too much downtime. Also, crest factor analysis, like many distortion measurements, is prone to interference from background noise. This is particularly challenging in a noisy factory where intermittent loud noises, such as stamping machines, air compressors, or something being dropped, can trigger a false positive. It also requires significant care and effort to correctly establish limit curves for optimum performance. So let's talk about our new algorithm that we've just introduced. This is more accurate and reliable than current methods, including our own earlier algorithm, and has other benefits. We've designed it so that you can view and listen to both the raw captured waveform and also the loose particle waveform without the stimulus. This makes it easy to correlate the measured results with what you hear, and also makes it easy to set limits based on audibility. 20 years ago, when we were transitioning from human listeners to automated measurements, most production line operators knew what a good and bad speaker sounded like. Most younger engineers today are only familiar with automated testing. So it's really important for test system manufacturers like us to have a way of correlating measurements to audibility. It's also much easier to set limits with this new algorithm. There are only 2 parameters to set, and the default values work well in most cases. And of course, the ability to listen to the loose particles while viewing the data really helps with setting meaningful limits based on audibility. This algorithm also expands the range of applications. Our original algorithm was specifically developed for measuring loose particles in loudspeaker drivers, and this new version is much better as well for measuring rattling parts, such as buttons, fasteners, and loose wires on various audio devices. It's also good for measuring impulsive distortion or buzz, squeak, and rattle in automotive audio applications. Let's take a look at the new algorithm. The basic time envelope analysis method is similar to our old algorithm, but rather than filtering and counting transients, additional analysis is applied to measure the prominence or impulsiveness of the detected artifacts. Here's a schematic, and I'll talk through each of the stages. We start with our unique stepped sine stimulus called STWEEP, which has a smooth transition from one frequency step to the next. This avoids any transients introduced by changes in stimulus frequency that you sometimes get when a step sine sweep is used. Since this is the same stimulus we generally use for other end-of-line tests, we can measure loose particles alongside other metrics with no increase in test time. We capture the waveform. You can see that here. This is just the raw recorded acoustic waveform, exactly as captured by the microphone. And right here, you can see the loose particle distortion. Next, we remove the fundamental, just leaving the loose particle and distortion artifacts. And what's neat about this is that we can play this through soundcheck on a reference loudspeaker or headphones to listen to the recorded artifacts and enable correlation to the measured results. So let's take a listen. Here is the stimulus signal. Now here's the response signal. If you listen carefully, you should be able to hear the transient distortion. Now this is the really neat part. We can listen to just the defects by playing this waveform with the fundamental removed. So now we know exactly what loose particles and distortion sound like. This is really useful for a couple of reasons. Firstly, it really helps understand what distortion sounds like, and it helps correlate algorithm results to audibility. But perhaps more importantly, it enables you to set meaningful limits based on defect audibility. Okay, let's go back to our schematic. Next, we're going to apply an envelope analysis, and this results in a time domain measurement showing the energy in the recorded waveform plotted against time. You can see the transient defects as these random bursts of energy. Now we calculate the prominence of each peak. Let's talk about this for a minute because this is what's really new in this algorithm. Here's Rahul, our DSP engineer, to explain.
Prominence is an established mathematical concept used in other branches of science, most commonly topography, and we believe we are the first to apply this concept to audio measurements. In a topographic context, prominence describes the elevation of a summit relative to its surrounding terrain. This differs from its overall elevation, which measures the height of the summit above sea level. Our research determined that the prominence of a peak in the waveform, calculated by comparing the magnitude of a peak relative to the surrounding minimums, reflects the impulsiveness of the distortion artifact more accurately than the absolute magnitude of the peaks. So in this algorithm, we calculate the prominence of each event in the time envelope, which results in a numerical magnitude for each. We then set a prominence threshold. That's the level above which the event will be counted as a transient artifact. You can see this threshold here as a red line on the graph, and we have also highlighted the events above the threshold in red. In our evaluation, we identified a threshold of around 10 dB as a good starting point. This may vary depending on exactly what device is being measured and the acceptable tolerance for the product. And remember, to help with setting limits, you can play back the artifact waveform to correlate the prominence level with audibility.
In the last stage of the algorithm, we count the number of events that exceed the threshold over the measurement duration. This gives us a numerical output that we use to set a pass-fail limit. This helps us eliminate false positives due to transient background noises. Typically, factory background noise events only occur once or twice during a quick measurement, whereas many loose particle transients will occur during the same time frame. So we can set the event count minimum to exclude infrequent transient background noise events to get reliable results under a variety of conditions. So that's how it works. Let's just summarize the benefits. Number one, it differentiates random transient distortion from periodic harmonic distortion, and this helps you troubleshoot production line issues quickly with minimal downtime. Number two, limit setting is straightforward. The measured metric is a loose particle count in a given time frame, so it's a simple numerical limit rather than a curve, and of course, it's not frequency dependent. You can also listen to the loose particle waveform to ensure that your threshold limit correlates to audibility. Number three, false positives due to background noises are minimized because the algorithm relies on a cumulative event count rather than a single event triggering a fail. Let's now take a look at some typical results for a good speaker and one with loose particle defects. This is my good speaker. Let's take a listen. I don't hear any transient distortion, do you? Now I'm going to play it again and capture the response signal. This is a very simple setup I have here, pretty much what you might use on a production line. An SEM measurement microphone, an Amp Connect 621 audio interface that includes a built-in speaker amplifier, and of course sound check. Okay, so for the good speaker, let's look at the output from each stage in the algorithm. Here's the waveform. Let's take a listen. And here it is with the fundamental removed. And the envelope analysis, the prominence, and finally the loose particle count. We're using the default values of 10 dB threshold and a minimum particle count of 5. This actually works very well in the majority of cases. Now let's repeat that with a speaker that we know has a loose particle defect. Let's take a listen. Can you hear the distortion? Now let's listen to the waveform with the fundamental removed. Can you hear that better? We're listening to just the loose particle distortion. Now let's compare that to the good speaker. You can see that makes it quite easy to hear the difference. Now let's look at the envelope analysis. You can see much more activity here with this bad speaker than with the good speaker. And finally, the prominence. You can see these large spikes here correlate to the most obvious transients. And you can see the loose particle count is much higher than in the good speaker. So there we have it. This new transient distortion method, known as the enhanced loose particle algorithm, significantly improves the accuracy and reliability of transient distortion detection. It measures transient distortion separately from harmonic distortion. It is more accurate than Listen's earlier algorithm, and it minimizes the risk of false positives due to background noise that is inherent with other measurement techniques. It's also easier to set limits than other methods. It works well in applications beyond driver testing, such as buzz, squeak, and rattle in cars, and rattling components in audio devices. Lastly, the way that you can play back just the loose particle recording and compare it to the visual representation clearly demonstrates the correlation between measurement results and audibility. This helps not only with setting limits, but also better understanding distortion measurements.